The air systems are to thank for much of what goes on in a commercial aircraft. You can imagine with an aircraft of this size, the system would be quite complex. At one time it certainly was, as a third crew member was required to operate earlier versions of the aircraft. Many of these aircraft, in fact, are still flying today. Now with modern automation, like what we have seen in the glass section, the systems are laid out in a way that makes operation of the system manageable by a two-man crew. The air system is a major part of this aircraft. It is partly responsible for passenger comfort, pilot comfort, engine start, equipment cooling, pressurization, and some anti-ice operations. Bleed air is the essential component of the 747-400 air system. Bleed air is essentially air pressure from the engine's APU or ground air source. Of course, this is explaining it in the simplest of terms. Just remember that bleed air is the life force of this system. Bleed air is used for air conditioning, pressurization, wing and engine ice, engine start, leading edge flaps, aft cargo heat, cargo smoke detection, hydraulic reservoir pressurization, potable water tank pressurization, air-driven hydraulic demand pumps, and thrust reversers. Engine bleed air is supplied from either the intermediate pressure or high pressure section of the engine. IP would be used for high engine power settings, while HP would be used for descent and other low power situations. The bleed air system is protected by a pressure regulating valve, PRV, which protects the system from excess pressure. Temperature protection is given by a fan air pre-cooler, which regulates the bleed temperature. Logic has it that with an engine bleed valve switch on, bleed air will open the HP bleed valve. The air then travels through the PRV, which will only open with sufficient pressure. The air then splits into the bleed air duct. The engine bleed air valve regulates normal pressure in the bleed air duct. It also prevents reverse flow of air, except during engine start. When pressure in the bleed air duct is higher from another source, the lower pressure engine bleed valve is shut to prevent reverse flow. During an engine start sequence, the engine bleed valves open to allow reverse flow of air to open the start valve. At this stage, the PRV is positively shut, as to not allow air in the compressor sections of the engines. If the start valve is even partway open, the PRV will be shut. After the N2 rises past 50%, the start valve closes, which allows the PRV to open, and reverse airflow is then prevented. Confused yet? Most are in this stage. It'll take a couple run-throughs in your head and some hands-on experience. This will come later. For now, let's go over the bleed air controls. Two isolation valves are available, left and right. These switches have two things we need to watch out for. First is the amber light, which if illuminated, tells us the valve position disagrees with the switch position. Second is the bar on this switch, which if on, the valve is open. When the APU is running, the APU bleed air switch is open. When off, the bleed valve is closed. In other words, engine pressure overrides APU pressure and defeats any need for APU bleed air. System fault lights on the overhead will show amber if a problem occurs, but usually the crew monitors the ICAS rather than the overhead. An engine bleed air switch is available for each engine. When on, the bleed air valve opens for engine start and the PRV and HP bleed valve open by system logic when pressure is available. In the off position, engine bleed air switches command the engine bleed valve, PRV, and HP valve closed. However, PRV will open with nacelle anti-ice and HP and PRV will open with thrust reverse. Knowing whether this system is off or not takes one glance at the ICAS. The bleed air system is very straightforward. Now on to the pressurization system. The pressurization system is nearly all automated and requires little input from the pilots. If an abnormal situation were to occur, it's important to know how to manually run this system. It is also very important to have a visual reference to what the system is doing. Maximum cabin altitude is 8,000 feet. The pressurization outflow valves work to always keep the aircraft comfortable. For example, just before rotation, slight positive pressure is made as to make the transition to the cabin climb pressure comfortable. Most of the time, the FMC looks ahead to plan and compensate ambient pressures for smoother cabin pressure changes. Even with one of the outflow valves completely inoperative, automatic control can still be done with just one outflow valve. Additionally, with one valve inop, only 2 packs are used. Let's get familiar with the controls for this system, because things won't always go as planned. When manual operation is needed, we'll need to know how to handle it. The landing altitude switch, when pushed, changes the mode between automatic, being the default mode, and manual mode. In automatic mode, the landing altitude is set by the FMS. In manual mode, the landing altitude selector will select the appropriate altitude as per pilot input and will show on the primary ICAS. Manual landing altitude is used when the landing airport is not in the database. 2 outflow valve manual switches, when on, will place the outflow valves in automatic mode. The means for this manual control is between these 2 switches. Outflow valve position indications are given above each outflow valve manual switch. The cabin altitude auto selector is usually left in auto mode. In this mode, cabin altitude controllers are switched on alternating flights between A and B. If the pilot wishes to manually select a controller, he or she may do so by turning the selector to A or B. The pressurization system is simple and straightforward, even when not in automatic mode. Things are about to get pretty tricky with the air conditioning section. The air conditioning gives us a mix of conditioned bleed air and recirculated cabin air to give us a controlled temperature throughout the aircraft. Pack control, zone temperature control, cabin air circulation, fault detection, and overheat protection are all automatic. Backup systems are used in the unlikely event of a system failure. On the main overhead panel is found the ECS control, longhand meaning Environmental Control System. First we will run through what each switch does on the overhead, then we will move over to the upper ICAS ECS page to learn about the various indications. Starting from the top, we have the Passenger Temperature Selector. This one switch automatically controls master temperature for all zones in the aircraft. C for cold and W for warm. This knob can be rotated to change the temperature. Temperature regulation is done by adding hot trim air from the bleed system to regulate the temperature zones. When this system is in alternate mode, pack output gives an average temperature of 75 degrees Fahrenheit. Much like the passenger temperature selector is the flight deck temperature selector. Operation is automatic. When changed to the 6 o'clock position, the spring-loaded selector can then be moved towards C for cold or W for warm for manual control. The zone reset switch will illuminate with a zone duct overheat, master trim air failure, trim air off, or master trim air valve closed and pack air continues to flow. This switch, when pressed, will reset the zone temperature controller if the fault no longer exists. With the trim air switch on, zone trim air valves and master trim air valves are controlled automatically. Thank goodness, that sounds complicated. With the trim air switch off, temperature is regulated by the passenger temperature selector in auto. Recirculation fans allow the air system to reuse some of the cabin air to reduce workload on the engines in return for some fuel economy. Normal operations call for these switches to be on. Off, the switches are off. The aft cargo heat switch, when on, allows bleed air for the aft and bulk cargo. A temperature control valve then opens and closes to manage temperature. Off, logically, the aft cargo heat is off. Equipment cooling is a very important aspect of the aircraft's air system. Cooling and airflow for the flight deck, and electronic and electric E&E compartment equipment racks. Cool cabin air from the lower fuselage is circulated through this system, and the warm exhaust ends up in the forward cargo area, which in turn keeps that area's temperatures regulated. On the ground, the system is kept in the normal position. In this position, the warm air is exhausted overboard through a ground exhaust valve. When one or more engines on each wing is operated on the ground, the system is configured for flight to allow for cabin pressurization. In flight, the inboard exhaust valve opens and operates the system as discussed before, pushing warm air into the forward cargo. If equip cooling shows on the ICAS, equipment cooling is not configured for flight. Placing the equipment cooling switch to standby will configure the system for flight. In override mode, ground and inboard exhaust valves are closed and air cooling is provided through panel air only. Now for what controls the air, the pack controls. The pack high flow switch places all packs in a high airflow position. Off, pack airflow is controlled automatically. The pack reset switch will reset packs after they have been automatically shut down after the fault no longer exists, and then resets the system that reset it in the first place. Knowing when there is a fault with the packs is simple by looking at the pack system fault light or various ICAS messages. 3 pack control selectors are available. In the off position, the pack valves will be closed and the pack protection systems are reset. In the normal position, pack control A and B are automatically selected on alternate flights. If one controller has failed, however, the other will automatically enable. Selecting A or B would select that controller unless it is in-op. In that case, the other control would be automatically selected. With one pack off, the other 2 packs will go to high flow. The ECS can be displayed on the lower ICAS or on the ND. We will now go over what each symbol means on this screen, but as we do so, keep in mind that what you are seeing on this screen may not represent the actual airflow of the system. Zone temperatures are seen here for all zones. The target temperatures are seen on the left, and the actual temperatures are seen on the right. The pack control is seen as off, A, or B, depending on what pack controller is being used, if any. APU bleed air isolation valve is seen here and indicates open or closed. The external air indication shows if a pack is operating with the engines off and APU off. The indication remains momentarily after external air is removed. Outflow valve position is seen here. The outflow valve control source shows whether we are under manual or automatic mode for that valve. A high flow indication will be seen here when under high flow mode. Wing anti-ice indications are shown here. Isolation valve indications show whether the isolation valve is open or closed. Engine bleed air valve indications are shown as opened or closed here. Nacelle anti-ice indication is shown here when anti-ice is on. Duct pressure and cabin altitude indications are more ICAS digits to look out for. This is displayed when the landing altitude is manually selected, when cabin altitude warnings are shown, cabin differential pressure is in caution, or when ECS or engine is selected on the secondary ICAS display. Bleed air duct pressure, much like the ICAS ECS screen, is white 12 psi and above, and amber 11 psi and below. Cabin altitude is shown here. Landing altitude is shown here, unless both cabin altitude controllers fail, or left and right outflow valves are both in manual position. Landing altitude selection is white when automatic, and amber when in manual mode. Cabin rate of climb is shown here. Cabin differential pressure is shown here. That completes the air system. As you can see, this air system is very important, especially for passenger comfort. With that in mind, there are also several flight critical operations that the air system provides for. Knowing this system is of the utmost importance. Next, we will discover the anti-ice and rain protection systems of the aircraft.